Welcome everyone. Good morning. My name is Tanveer Alvi. I'm the training coordinator at Clearwater. Thanks again for joining this webinar. I'll quickly, without wasting any more time, start with the acknowledgement of country. So Clearwater acknowledges the Wurundjeri Woiwurrung people as the traditional owners of the land from where we operate. And we pay our respect to the elders past, present, and the elders and people from other communities who might have joined us today. So just a bit of a general housekeeping. As you know, the session is being recorded. I'll request you all to keep your microphones on mute and keep your video cameras off while the presenters and speakers are presenting. There are chat and Q&A functions. Please feel free to use them. Use the like button and the Q&A section because the questions with more likes will be given preference. We'll also have a dedicated Q&A session afterwards, after the presentation. And if you like, you can raise the virtual hand. You can see the icon on the top strip there. And if you do that, I will try and find you in the list and unmute you so you can ask your questions through the microphone. There will be breakout rooms during which you'll have your microphones and cameras on, and you'll be able to ask questions or comment or talk with the speakers. So just a quick look at what these 2 hours will look like. So shortly, we'll be starting with the presentations. The presenters will talk about the hydrology, water quality, ecology, and the social science. Afterwards, we'll have the Q&A session, following which we'll have a short break, about 5-10 minutes. After that, we'll come together again, and we'll have the panel discussion facilitated by Belinda Hart. Afterwards, after the wrap-up session, is when we'll have our breakout rooms. Now, after the breakout rooms, this session will close, but feel free to come back to this main meeting. Now, the breakout rooms will work a bit differently. I will be posting links for all different breakout rooms into the chat. So choose your own room where you want to go and just click on that link. Now, just keep in mind that these links will take you to a different meeting altogether. So if you want to come back to the main meeting, you'll again have to click on the main meeting link. I'll share that in the chat as well. So a bit about Clearwater, who we are and what we are doing here. So Clearwater is a program which is hosted by Melbourne Water and funded by DECA. We are a capacity building program for integrated water management, and we've been working since 2002. Our goal is to develop skills, share knowledge, and build networks. So we work with government organizations, private consultants, developers, engineers, and officers who are in this field, in the IWM field. And we provide support in the form of trainings, workshops. We also organize industry site tours and lots of different networking events. We have a huge online library. I have a small inset over here. So that is what our present resource library looks like. As you can see, we have case studies, fact sheets, presentations, video gallery, and trust me, there's a huge number of resources, and this huge amount of data on the website is one reason that we are moving to a new website, which is really exciting. So in a couple of weeks, if you visit our website and if it doesn't look familiar, if the logo looks like this and the color palette looks like that, that's because we are rebranding and having a new website. You can still follow us on LinkedIn to keep up to date with all the changes. Well, coming to our presenters, I'll quickly introduce Dr. Mathew Burns. He's a senior research fellow at the University of Melbourne, and I'll share a few details about him. So as I mentioned, that he's a senior research fellow at Melbourne Uni. He's internationally recognized for his research in urban hydrology and stormwater management. He has 80 publications and over 4,500 citations, and his work highlighted the problems of urban stormwater runoff and advanced the understanding of flow ecology linkages, leading to better protection and restoration of our waterways. We also have Dr. Darren. He's a senior research fellow at Melbourne Uni. His work has focused on the application of whole of catchment management of stormwater. He also supports the delivery and adoption of Melbourne Waterways Research Practice Partnerships research program. And recently, he's been co-supervising PhD students investigating platypus behavior in Bournemouth Creek. Wow, I would like to get on that program. So without any further ado, I'm handing it over to Dr. Darren Bose. Stop sharing my screen so that you can share your presentation.
Yep, and I'll unmute myself. That was always helpful. Right, so just checking that people can see that. Yes? I don't know if anyone can see that.
Oh, yes, we can, and we are getting lots of thumbs up.
Okay, good. Sorry, I didn't see the thumbs up elements there. Let me just get that back. All right, so thanks everyone for joining today. I have quite a challenging task ahead in that I need to present in 15 minutes details of two quite complicated projects that took, I think, collectively around 15 years to complete. Spent millions of dollars and involved hundreds and hundreds of people. So as you can see here, I'm presenting on many of those people involved in these research projects and the delivery of these projects. Because we have quite a diverse audience, I am going to start by giving a little bit of a background on the issues of stormwater. I think we have some people in the audience who have don't have a background in stormwater management. I'm also going to talk a little bit about the solution to that stormwater problem, and then I'm going to dive into a little bit about why we undertook these projects and what work was completed in each catchment. And of course, that's leading us into the real reason why you're all here, and that's to hear about some of the results from our project. So let's start with a little bit of that context. When we urbanise a catchment, we build roads and roofs, and then we typically install a whole range of stormwater pipes and pits to drain away any rain that falls on that catchment on our newly built roads and roofs, and drains away as stormwater. And those pipes are very, very efficient at delivering the water directly to the creek. And this completely changes the way in which water interacts in a catchment. So in a forested catchment, when rain falls on the creek, when rain falls on a catchment, we see that most of the water is lost through evaporation or transpiration. A reasonable amount enters in through the soil and flows to the creek as base flow, and very little amount of rain actually runs over ground and into the creek directly. Compare that to our urbanised catchment, we see a complete reversal of those figures. Now, most of the water is actually delivered to the creek as runoff, and it's delivered very quickly and with a lot of force. Some water is lost through evaporation and transpiration, and very little amounts of water actually flows into the soil now because we've sealed a lot of the surfaces, and very little is delivered as base flow. And what this does is it completely changes the hydrology of a catchment, how much water gets to the creek, how quickly it gets there, and the energy in that water when it arrives at the creek. So in this stylized hydrograph here, we can see that in an urban catchment, when we have rain, we get really quick, someone's got their mic on too, if they can just check your mics. We can see that we get really quick rise in flows or water depth in the creek, high peaks, and then quite dramatic drop off in flows as well. We also generally have a very low base flow in the creeks. Compared to a forested catchment where we see that after rain, those peaks are much slower to form, and they're much lower as well. And then they also have a longer tail, so they hang around for the flows that are a lot more steady. And what this change does is that it leads these sort of really high energy, high flashy flows in an urban catchment, leads to severe erosion within the creek. The creek itself becomes quite channelized and it loses engagement with the floodplain. We get a lot more mobilization of sediment, and the water becomes a lot more suspended sediments in the water. That generally leads to a loss of habitat within the creek, and then we start to see a decline in the biodiversity, particularly with those species that are sensitive to these changes or that are used to having these such more moderate sort of flows and higher base flows. If you add on top of that, of course, stormwater pipes and pits are very, very efficient at collecting pollutants and litter and delivering those into the creek as well. So you get this mix of dirty water and changes in hydrology all affecting our creeks. Now, this is a very well-studied phenomenon across the world. It's not just exclusive to Australia. It's Also well studied is the application of stormwater control measures to address this problem. So stormwater control measures are any asset that effectively is constructed in a catchment that helps reduce those peak flows, return base flow to the creek, and also improve water quality. So they can include things like, but not limited to, rainwater tanks, rain gardens, or vegetated infiltration basins as well. So those stormwater control measures have been very well studied as well, and they've been shown to have really positive impacts on the hydrology and water quality of stormwater at a local scale. But prior to the Little Stringybark Creek and the Dobsons Creeks projects, there remained a question of what would happen if you applied this across the catchment? How effective would they be if you did it en masse rather than just at the allotment scale? And in short, that's essentially what these projects were designed to answer this question. Can degraded urban streams be restored by application of dispersed stormwater control measures? Specifically, the goal or the target of those projects was to install as many stormwater control measures as they could in those catchments, jam them in as many as they could fit in. Obviously, that was within the constraints of funding that they had, space, and time. But the real goal was to treat well as they could, as much impervious surfaces as possible. So those hard surfaces that were impacting upon the creek. So why did we choose Little Stringybark Creek and Dobsons Creek? So this is sort of an artist's impression, you might say, of a graph that is found in a lot of science. So it doesn't look very accurate, but believe me, it is. But what this graph shows is that it doesn't take a lot of effective imperviousness in a catchment. So those areas of sealed surfaces draining to the creek. You only need a little bit of imperviousness installed in a catchment, and you see a dramatic decrease in the health of a stream. And then it doesn't really matter how much more imperviousness you put along in that catchment. Effectively, you've already done all the damage that you're going to do. But what this journey does mean is it's much harder to get a restoration along. So if you're starting out here, it's a lot harder to see or have any influence on the health of the creek. So as you might be suspecting, these two little orange dots here represent Little Stringybark Creek and Dobsons Creek. So they were chosen because they're effectively at this tipping point. They are degraded creeks, but the catchments aren't so heavily urbanised that there's not an opportunity to address that issue and hopefully see an improvement in the health of the creek. All right, so a little bit about the two projects. Little Stringybark Creek is in Mount Evelyn, east of Melbourne, in the Dandenong Ranges. There are about 1,100 properties in the catchment, of which about 830 are connected to and impacting upon the creek. Most of those are up here in the upper catchment. The lower catchment is mostly sort of rural residential properties, large rural residential properties. So mostly residential in these upper catchments. We have a small industrial site here, and we have a few schools as well, which are all big contributors to the issue of stormwater to the creek. There are 3 tributaries in this catchment, which is important, and Matt will sort of elaborate on that a little bit later on. So this project, Little Stringybark Creek, was led by the University of Melbourne, in collaboration with Yarra Ranges Council, Melbourne Water, and Yarra Valley Water. And it was funded through a combination of Melbourne Water, state and Commonwealth government funding, and also contributions from the private landowners. It commenced in 2008 and ran till about 2014, 2015. In that time, we installed stormwater control measures in just over 230 residential properties. So all of those properties had a rainwater tank, which was connected to internal supplies, so like toilet, washing machine, some hot water. Some of those tanks were also leaky tanks. So a leaky tank is a tank that has an orifice, a passive orifice that just slowly leaks water back either into the stormwater or onto some surrounding vegetation. A lot of our tanks also had infiltration trenches or some sort of rain garden, and that was to encourage base flows back into the creek as well. And the participation of residents was encouraged through a combination of education and incentives, but I'll be talking a little bit more about that in my second presentation after Matt has spoken. Of course, we also had to address the non-residential hard surfaces, impervious surfaces contributing to the creek's health. So we installed 90 non-residential stormwater control measures, and that include public reserves, roadsides. So roads are a big contributor to the problem of stormwater. Schools, the industrial side I mentioned earlier, and also the one petrol station in the catchment. So those non-residential stormwater control measures ranged in size from this large example here. This is at Morrison Reserve. So this is over 700 kilolitres of tank used for irrigating a nearby sports field. And then it overflows into a series of infiltration basins here. Also leaks out water during winter to provide capacity in the tank. So it ranged from that really quite significant high investment site to these much cheaper, sort of simpler systems. So this is just a small roadside vegetation infiltration rain garden. It's a mouthful. That's really just probably a few square metres in size, treating perhaps 100 metres of road. So for the Dobsons Creek, located in the basin, so also in the Dandenong Ranges, a bit smaller in terms of the number of properties impacting upon the creek, mostly residential for this catchment. But interestingly, this is quite different. The development is lower in the catchment, so the headwaters of the catchment are all forested, which is, I think, plays a bit of a story in our findings as well later. This project was different in that it was led by Melbourne Water in collaboration with Knox City and Southeast Water, and was funded primarily through Melbourne Water with some state government investment as well. And it was delivered between 2012 and 2017. They had around 250 residents, so a little bit more than Little Stringybark Creek. They only used tanks, but they had two types of tanks. So they had tanks for internal supply, again to toilet and washing machine, and they had some dedicated tanks, which were those leaky tanks, which were just providing storage capacity and some base flow replication as well. And they delivered their tanks through 2 rounds of incentives. They also did some non-residential works on streetscapes. They didn't do as many as Little Stringybark Creek. That was partly because they had quite a large, significant infiltration basin at the bottom of the catchment in Wicks Reserve. And so that did a lot, or provided a lot of treatment for the non-residential works as well, areas as well. So a really significant size system there. Right, so as you can imagine, we needed to assess if all of these works were going to have an impact. To do that, we developed quite a comprehensive monitoring program. And in this program, we compared our experimental streams with both healthy and degraded streams in the Dandenong Ranges. And we did that before and after our experiment. Specifically, we monitored some assets for their performance, so some tank monitoring, as well as some of our infiltration rain garden monitoring as well. We continuously monitored stream hydrology, and we occasionally monitored or intermittently monitored water quality, the macroinvertebrate community, diatom community, the benthic algal biomass, and leaf litter decomposition. And that monitoring continued from sort of 2008 or even prior, so we had some pre-works data as well, and up until 2022, although the macroinvertebrates data is still being collected as part of Melbourne Water's ongoing monitoring programs. As you can imagine, with such complex long-term research projects, there has been a lot of knowledge generated from this project. And this knowledge has focused not only on the key research questions around the impacts of stormwater on streams and the restoration of those through disconnection of the catchment, but also complementary research as well, such as how you engage with the community and local government, how you measure environmental impact and so forth. So lots of papers, lots of conference presentations, YouTube videos, reports, newspaper articles, you name it, we've kind of done it. But of course, all this is really culminating now in a series of fact sheets that we have prepared, and that's really the catalyst for today. So these fact sheets summarise not only the scientific findings of these two projects, but also the practical findings and insights. So based on reflections of the research team or the people involved in delivering these projects. And we hope that these fact sheets will help to inform and guide sort of planning and delivery of future waterway management projects. They cover a whole range of topics, so there's 10 of them in total, and we will be just talking about a few of them today. We'll have to talk about others perhaps at another event another time. And I think that's my 15 minutes. I don't know if we're doing questions now or we're holding off, or am I passing to Matt? I'm not sure.
I guess, yeah, if Matt can present now, and then we can take all the questions later on together.
No worries. Yep, good. Over to you, Matt.
Good job, Darren. All right. Can everyone see that, or?
Yep, we can.
Yep.
All right, thanks, Darren. Yep. So my job today is to talk through the hydrology, the water quality and ecological outcomes that we've observed so far, and sort of does feel like a bit of a privilege to talk through this today. It's really been as Darren said, the project's been a huge project, and we've had so many people at various stages, not only through actually building the works, but also through sort of analysing a lot of the data and research staff collecting hydrology, water quality, things like that. So as Darren said, from the monitoring perspective, the experiment was set up as a before-after control reference impact study. And so what that meant is that it meant that we had some streams in really good ecological conditions. So these are streams in the Dandenong Ranges, so Sassafras Creek, Linda Creek and Lyrebird Creek. We also had some control streams. So the control streams are streams that are degraded by urban stormwater runoff, and streams that we didn't implement any stormwater control measures. So they were Brushy Creek in Mooroolbark and Ferny Creek in Ferny Creek. And we also had our experimental catchments. So catchments that are degraded by stormwater, but we've implemented works in the catchments to hopefully improve their condition. And so they were Dobsons Creek. So there were two sites on Dobsons Creek and Little Stringybark Creek. An important story of the Little Stringybark Creek catchment is that we monitored not only the main catchment of Little Stringybark Creek, but we also monitored three tributaries in Little Stringybark Creek, and we achieved sort of different levels of disconnection in those tributaries, and that's an important part of the story. So as Darren said before, I guess a lot of the basis for this project is this idea that if we can disconnect impervious areas, if we can improve the way we manage stormwater in these catchments, we might be able to improve the stream's ecological condition. And it's important to note that this study it's an example of a retrofit project. So probably sort of the hardest context to do this work. The theory with the project is that by implementing stormwater control, hopefully the ecological condition of Little Stringybark Creek and Dobsons Creek will start to sort of trend towards the condition of the reference sites and away from the condition of those degraded control sites. Another important feature of the experimental design is that it allowed us to make sure that if we see an effect in Little Stringybark Creek or Dobsons Creek, it's because of the improved stormwater control. It's not because of things like climate. All right, so I'm going to sort of talk through, I guess, some different responses that we think sort of should happen when we disconnect impervious areas and we reduce effective imperviousness. And then I guess sort of then highlight what we found from those various responses. So the main experimental manipulation is reduce connected imperviousness. So that's sort of what we set out to do. So when we do that, theoretically, we should see some hydrological impacts. So we should see things like reduced size and frequency of polluted stormwater runoff. We should theoretically increase base flows and their quality. As Darren said before, urban streams tend to have lower base flows. So through increased infiltration, we should increase those filtered flows and their quality. The changes to hydrology and improved treatment of stormwater should lead to some water quality impacts. So things like reduced nutrient concentrations, things like that. Of course, because we're slowing down stormwater flows and reducing that hydrologic impact, there should be some geomorphic impact. So things like reduced transport of coarse sediment. We should start seeing some more sand and gravels in our Little Stringybark Creek and Dobsons Creek. Changes to the hydrology and water quality should lead to some changes to in-stream ecology. So in terms of structural measures, so we might start seeing reduced algal growth, fewer nutrient tolerant species, more low nutrient adapted species. Maybe see some fewer tolerant algal grazers and more sensitive animal species, so increased biodiversity. We might see some improved ecosystem function measures, so reduced microbial leaf breakdown and increased shredding of leaves by invertebrates. And finally, some other measures of ecosystem function. So we might see some increased retention of nutrients within the stream itself. And again, just to reiterate, I guess the whole basis of this is reduce connected imperviousness, and then all these other responses sort of should follow on from that. So the first sort of, I guess, result to talk through is, did we reduce connected imperviousness in these catchments? And we did. So this is just a plot showing effective imperviousness over time for these reference control experimental catchments. We can see, I wonder if I can get a mark. I'll try. We can see, can everyone see this line, maybe? I'll assume you can. You can see, you can?
Oh, yes, we can. Yes, we can.
Yeah. That's great. So you can see, for example, our effective impervious area for our reference sites, our streams in really good condition. You can see the effective imperviousness is very low. It hasn't changed over time in here. But what's really important, and we can see here, is we can see that for our experimental sites, we can see effective imperviousness sort of starting, I think this is Little Stringybark Creek here. It's starting at around 8%, something like that. And as we've implemented rainwater tanks, rain gardens, we can start seeing that effective imperviousness drop. Which is great. So for Little Stringybark Creek, we started off at around 8%, and at the sort of completion of the major works, we ended up at around, I think, 6%, that's 5%, something like that. But one of the tributaries of Little Stringybark Creek, the northern tributary of Little Stringybark Creek, we started at about 6% effective imperviousness, and we did a really good job there. So we ended up at around 1.5 or 2% effective imperviousness, which, a sign of, huge amount of effort there, by Darren, by Yarra Ranges and Knox to have a really good reductions of effective imperviousness. Reductions that, at least theoretically, we should see some sort of impact in the stream. And just another thing to quickly to say that, so we reduced effective imperviousness area, effective imperviousness, but the way we measured reductions in effective imperviousness took into account the performance of the stormwater control measures that we implemented. And that was a really important piece of work that Chris Walsh, a colleague, led, because you can imagine that if you have a rainwater tank that might not have much demand to it or isn't performing very well compared to a rainwater tank that is performing really well, obviously their ability to sort of effectively disconnect that impervious catchment is going to be quite different. And that's why it was really important that we spent a lot of time in measuring, modeling the performance of these different stormwater control measures, and including that modeling and that performance in the way we actually assessed our measurement of reductions in impervious area. And there's a fact sheet there, I think it's fact sheet 8, which talks about that. All right, so coming back to our responses, so we can give a tick that we reduce connect imperviousness or effective imperviousness. I'm now going to sort of talk through some hydrology results now. So did in the experiment, did we reduce the size and frequency of storm flows? And so we had a former student, Sung-Ying Lee, who sort of was a critical component of this hydrological assessment work. And there's a journal paper that is close to being published, which sort of talks about these results. So in our urban catchments, we know that we only need a small amount of rainfall. A small amount of rainfall causes a big sort of pulse of stormwater, and that's what Darren started off the start of his talk talking about. And so for our urban sites, we have some rain. That rain generates a big pulse of stormwater. We can also, I think this is still going to work. This marker here. So small amount of rain causes a big pulse of polluted stormwater runoff. We can also call that quick flow or direct runoff. So this shading in blue here is our quick flow. And we can also see that when this impervious runoff is conveyed to the stream via the pipes, we also see this big peak flow here. That's a storm event. Theoretically, when we implement stormwater control measures, we should see quite a different hydrograph or flow response. And so when we implement these stormwater control measures, we should theoretically have a lower peak flow here. And importantly, we should actually have a much smaller volume of quick flow, this blue here, because we're retaining water, we're harvesting water, we're infiltrating water. And so the whole basis of this hydrologic analysis was to see in Little Stringybark Creek and Dobsons Creek, have we reduced the volume of this quick flow in storm events, and have we also reduced these peak flows? And so to sort of answer that question, we did some statistical analyses. And so this former student, Sung-Ying, spent, I think, 3 months of her life here identifying 6,500 storm events across our study catchments. And so from each of those storm events, we calculated quick flow volume, so the amount of essentially the amount of impervious runoff or stormwater generated following rainfall events, and also calculated peak flow. We developed a statistical model that was run in this R, which is some computer software that we can do these statistical tests in. And when sort of running these statistical models, we included things like the effect of the stormwater, the SCM effect. So we basically captured all the rainwater tanks and rain gardens and other measures that were implemented. And of course, took into account other things like rainfall, antecedent conditions, and things like that. But basically, this statistical model allowed us to be, pretty confident, to know whether these measures had an impact on the hydrology. So I'm going to talk through some of the results now. So we found that the rainwater tanks and all the other stormwater control measures reduce quick flow for small rainfall events, which is great. I wish we could have some celebratory balloons or something. And importantly, we found that the strongest effect that we saw was at this tributary that had the highest level of stormwater control. And in this particular tributary, almost all the impervious surfaces drained to some kind of stormwater control measure. And just as an example, for a 3 millimetre rainfall event, we ended up getting around a 61% reduction in quick flow volume. So that was really positive. And of course, we still observed some other in the other catchments, experimental catchments, we did see reductions in quick flow volume, but they weren't as strong as what we saw in this northern tributary. And so a really big sort of reason for this reduction is because the project had a really strong focus on stormwater harvesting, on retaining stormwater in the catchment. And so lots of rainwater tanks connected to, at the household scale, a lot of these tanks were used for toilet flushing, clothes washing, hot water usage, outdoor irrigation. There were some really large tanks. So these are, as Darren said, 750 kilolitres of storage and water used to irrigate 2 really big ovals. So this really strong focus on retention was a key reason why we saw these results in terms of reducing quick flow volume. So in terms of, so that was quick flow volume. In terms of storm event peak flows, we also found that the stormwater control measures reduced peak flows. And in particular for this, this tributary where we had highest levels of disconnection, we found that there were near reference peak flows for up to 12 millimetre rain events, or 86% of the days. But in other words, for most rain events, the peak flows in this particular tributary, hydrologically, they were almost similar to what we saw in our reference condition stream. So another really good result there. And the effects that we saw on peak flows were clearer across all catchments compared to the results for quick flow volume. And so while we got while we got stronger results for at least for peak flows, is because all the systems that we built, they might not provide high levels of retention, but all the systems provide good levels of detention and attenuation. And so, example, for rainwater tanks, there's always going to be some detention provided above the overflow pipe. And similarly with rain gardens and some other measures, these systems can work quite well for attenuating peak flows. And so that was sort of, at least hydrologically, why we saw probably stronger results for peak flows. So just a quick discussion around the hydrology. So we found that our stormwater control measures can alter urban flow regimes in the context of a catchment retrofit. So we saw reductions in quick flow and peak flow at the catchment scale. And I guess our strongest evidence on that was when implementation intensity was high. Just to quickly say that the real reason that we saw these results is that these stormwater control measures were, they were designed to with hydrologic objectives in mind. So we designed these measures to reduce the frequency of runoff delivered to streams, reduce stormwater runoff volume, increase filtered flows or increase base flows. And we really also tried to capture runoff from all impervious surfaces in the catchments. And these sort of principles that I've just been speaking about, they were published in a paper that we can send around. Another important part of the results is that the results were dependent on the rainfall event size, and so we found that the stormwater control measures were most effective at the small frequent rainfall events. But that's really important because we think that the primary stressor to in-stream ecological values is these frequent rainfall events. And of course, in very large events, there were diminishing returns because the measures obviously have this idea of limited storage capacity. And why this is important, so this is some work that my colleague Tim Fletcher did. Tim basically showed that if you can retain even like say 5 or 10 millimetres of runoff, you can get some really big reductions in how many days of runoff per year stormwater is delivered to the stream. And so, for example, if you can retain, say, 10 millimetres of runoff, you can reduce the days of runoff per year from sort of 95 days to 20 days a year. So even capturing small amounts of runoff can have a really big sort of impact. Another point about the hydrology, just to talk about, is that so we've seen these hydrologic results in Little Stringybark Creek and Dobsons Creek. Probably a word of caution that we can't easily just sort of transfer these results to another catchment. Obviously, all catchments are different. The catchments we've worked in, the soils, for example, are quite clayey. If we were to do this project in a catchment with sandy soils, the results would have been different. Another point also is to make is that I guess this idea of completely returning flows from a degraded urban stream completely back to natural, probably going to be difficult. And one of the reasons why is that just through the process of urbanisation, things like the soils get changed so much, and sort of returning, getting back to those very high levels of storage and natural catchment is probably going to be difficult, but it's definitely still worthwhile doing. All right, so we've reduced the size and frequency of polluted storm flows. In terms of base flows, we're still doing analysis on that. So lots of infiltration. Theoretically, we should have increased base flows. We're still doing some work on that. We think through the water quality results, there might be evidence of increased base flows, but that we still need to do that formal analysis. Okay, so I hope I'm going okay for time. Maybe, am I, Darren? I can't see anyone, but
I don't know. Sorry.
Yeah.
okay.
Yeah, we still have like 10 minutes or 15 maybe. So yeah,
great.
we're good.
Okay, that's good. All right, so I'm going to talk now through the water quality results. So have we reduced nutrient concentrations because of the improved stormwater control? And so our colleague Chris Walsh, who a lot of you would know, led this particular bit of work. And so, yeah, I'm going to talk through the approach. So in terms of the water quality, so as Darren said, we monitored the water quality in our reference control and experimental sites. The water quality monitoring occurred over a pretty long period, so 18 years of monitoring. It wasn't sort of continuous for those 18 years. There were some little gaps in there, but a really large data set. So in terms of the water quality, we took regular samples. So we say I think I went out there occasionally, but we had a lot of other great staff who led a lot of that work. So we took sort of regular samples, so every month, every second week during dry flow conditions, but we also really aimed to during wet weather to try to get samples as well. So in the field, we measured electrical conductivity and temperature, but in the lab, so we collected water quality samples and we tested for total nitrogen, total phosphorus, nitrate and nitrite, ammonium, filterable reactive phosphorus, and total suspended solids. And we took those water quality samples to a lab in Monash University. And so again, we did a statistical analysis, and again, this was work that Chris led. So again, we had different predictors in this statistical model. And importantly, I'll get my mark again. These predictors included things like the SCM effect, so our measurement of reduced effective imperviousness. And things like antecedent conditions and rainfall. Again, we built this model, and so we tested. So we tested to see if whether the stormwater control measures had an influence on these response variables to the right here. And so in terms of the water quality, again, we had some pretty encouraging results. So we found that the stormwater control measures reduce nutrient concentrations under low flow conditions. So we found that total phosphorus and filterable reactive phosphorus were reduced. And for some sites, so again, for this site that had very high levels of treatment, concentrations of these nutrients approached reference levels in dry weather. We also found that total nitrogen and nitrate and nitrite were reduced, although the responses for these predictors was a bit more variable, and it was sort of confounded by the fact that in these peri-urban catchments, there are quite a few septic tanks, which are old and leaking, and sort of confounded the results a little bit there in terms of the nitrogen story. Another water quality result related to temperature. So we found that the stormwater control measures improved the thermal regime in these experimental sites. So our urban sites without stormwater control measures were sort of 4 to 5 degrees warmer than our reference site. So quite a difference there. But importantly, installing the rainwater tanks and rain gardens reduced in-stream temperatures towards the reference condition, especially in summer low flow. So potentially a really good result there. In terms of some of the other results, there was a mixed or no response for some of the other variables. So for total suspended solids, we didn't detect any effect of reduced imperviousness. And we think there could be some geomorphic reasons why that's the case. Some resuspension of sediment from the stream banks. In terms of electrical conductivity, we actually, our salinity, we found that increased with the installation of the stormwater control measures. We're still working through that, and it could be that because we've increased infiltration and groundwater flows, that maybe some cooler groundwater, cooler but salty water is getting flushed into those systems. So just a bit of a discussion around the water quality. So it's pretty cool that the water quality impacts are reversible. So we can see improved in-stream water quality by implementing stormwater control. But similar to the hydrology, the strongest effects that we saw occurred in the catchments where we had substantial intervention. And one of the really important reasons why we've got these good water quality results is through some of these systems that Darren spoke about that were at the end of catchment. So these sort of systems providing sort of a final treatment of water before discharge into the waterways. And so, a really good example of that is the Wicks Reserve Rain Garden, which is in Dobsons Creek, a really large rain garden. I think its claim to fame is the largest in the Southern Hemisphere. But it's doing a really good job of providing a sort of final treatment effect. And there's a lesson in terms of for future developments where you can to reserve some space near the where the pipe outlets are to the stream for that final treatment. Another point, just to quickly say on the water quality, achieving sort of improving water quality probably a bit easier than achieving some of the flow objectives. Systems can be built a bit smaller and still get really good water quality performance. But I'll just say that if you can design stormwater control measures that meet the flow targets, then by doing that, you're going to meet the water quality targets for sure. So, and another sort of, I guess, discussion point there in this project is this our legacy impacts. And so we saw that our results for total nitrogen and nitrate and nitrite were confounded by septic tanks. And I guess depending on where you are, that might be an issue. All right, so we're getting through this this sort of flow chart here. So we can give a tick to improving water quality. In terms of reduced transport of coarse sediments, we need to do a bit of work to confirm that, but there is some evidence that through reduced flow velocities and things like that, that we have seen some more sand and gravel in the main catchment for Little Stringybark Creek, but we need to do a bit more work on that. So in terms of the ecological results, I'm going to talk through some of those now. They're probably we've got some preliminary results on that, and we're continuing to work through the data, but I'll talk through what we've got so far. So in terms of the stream ecological results, so far we haven't seen any change in some of the standard biotic indices. So things like signal score and LUMAR score, these are macroinvertebrate family composition metrics. And so far we haven't found any response into the stormwater control measures. But we have seen some underlying ecological change. So for Dobsons Creek, we've seen that the abundance of some monetarily sensitive taxa have increased. And so there's some evidence there of improved biodiversity. And we think that could be related to the fact that for Dobsons Creek, its headwaters are forested, whereas in Little Stringybark Creek, that's not the case. So some other ecological results, looking at diatoms. So we've seen little change in overall diatom index, but we have seen some shifts in community composition. So we've seen an increase in a more sensitive species, a species name that I'm definitely not going to try to pronounce, but we have and also seen a decline in several other taxa, which is evidence of greater community evenness. And so what that means is because the assemblages for diatoms are more even, that could suggest improved flow and water quality conditions, and so evidence of reduced environmental stress. But like I said before, a lot of these ecological results are results that we're also data that we're still sort of crunching through. So just a quick discussion on the ecology. So we've improved flow, we've improved water quality. It could be to really promote this sort of further ecological recovery that we might need to start thinking about doing some in-stream works, and so things like maybe some riparian planting to improve some habitat. Also thinking about putting some more coarse material into the stream. So maybe sort of injecting some gravels or coarse material in the stream. That might be really sort of important to support this recovery. A really key discussion point is that it's definitely not worth doing any habitat works before dealing with the stormwater problem. So if we were to just go and do some in-stream works without dealing with the catchment stressor, which is stormwater, then we just all those benefits are just going to be undo as these rainfall events occur. So in-stream works definitely have a role to play, but only once you've dealt with some of that stormwater impact. All right, so continuing on with our flow chart, we've a tick for some changes, positive changes ecologically, but more work needs to be done. And in terms of the last sort of component there in these streams retaining more nutrients, we still need to answer that question as well. So I guess I'm almost done. So just sort of thinking about some other points, I guess as part of this whole retrofit project, that if we want to really, I guess, fully restore these degraded urban streams, we really sort of need to get our head around this idea of trying to retain runoff from all impervious surfaces. we're not just a subset, and we've got really good evidence from that, particularly looking at this tributary where we're in this tributary where almost all impervious surfaces drain to some kind of stormwater control measure. Of course, as what Darren was getting to, there were some practical constraints which limited our ability to disconnect further. A really big constraint was limited public space for stormwater control measures. So we pretty much used up all council land, for example, that we could. So if we had more public open space, we probably could have actually built more stormwater control measures or built larger ones than we ended up doing. Another practical constraint was a partial uptake by private landowners. As Darren mentioned before, in Little Stringybark Creek, there were, I think it was about 800 households. We ended up doing works on around 200, 250, but there were hundreds of households that weren't engaged at all in this process. And another important constraint was that some systems were non-operational at times. So maybe 20 to 30% of some of the rainwater tanks failed due to things like poor maintenance, pumps failing, things like that. And in the end, I mean, we did an amazing job, I think, of particularly in this retrofit catchment of disconnecting stormwater. But there were still opportunities to capture more runoff, to treat more runoff, and to use more runoff. So another, I guess, key takeaway for practice, and I definitely this was a nice picture that one of the AGI tools helped me make. We tested this idea of improving stormwater management in the hardest context, which is the retrofit context, the existing urban catchment. But we showed that it can be done. So we can implement rainwater tanks, other stormwater control measures, if we design them to achieve certain hydrologic and water quality objectives, reduce runoff volume, runoff frequency, improve base flows, treats water quality, then we can see in-stream improvements in hydrology, water quality, and in-stream ecology. But in this particular retrofit example, we were limited by lack of participation in some cases, lack of space for systems, and we had trouble finding enough demand for stormwater. But the lesson here is that for new development areas, for greenfield development, we can design everything from the start to be perfect, in a sense that we can, for our new developments, we can make sure that we allow enough room for our stormwater control. We can make sure that, similar to what Southeast Water have done in Aquarivo, we can make sure that all new houses built have a rainwater tank that has a high water use, things like that. So a really important lesson there. So I guess to wrap up, would we do it again? We would, and we are. So Melbourne Water, in conjunction with the university, have started the next retrofit project in Monbulk Creek. And one of the key, one of the features of working in Monbulk Creek this time is that we're implementing smart or active rainwater tanks and stormwater control measures. So these are systems that use smart technology that can perform a lot better than passive systems. And maybe we can provide some links there to everyone surrounding this project. Perhaps in doing this again, we would build in financial rewards, things like some price signaling for management and maintenance, to really sort of encourage people to maintain these systems, or to get water retailers potentially to be involved in that maintenance. I guess another point that retrofit projects, they're so important, because if we want to see improved waterway condition around Melbourne, then we have to be working in retrofit catchments. We have to be working in catchments already developed. And that's, I guess, through this project has provided some really important lessons around things like improved planning, you know, if new buildings, new households can be required to improve the way they manage stormwater with these measures, you know, designed in a way that address these hydrologic and water quality stresses, that we might start seeing improved condition. Thanks, Jess. And I guess the final takeaway, and I sort of said it before, is that this Little Stringybark Creek and Dobsons Creek really gives us some great clues on how greenfield stormwater should be managed and how we can manage stormwater, you know, correctly from the start. So I think that's all I had. Thanks for listening.
Thanks so much, Mathew. That was really interesting and actually spot on time. So
Perfect.
we can, if Darren also wants to come online, thank you. We can start, I guess, the Q&A session now. So, Mathew, if you can turn your camera and mic on as well. So, that has disappeared now.
Sorry. Am I talking about community engagement now, or?
Yes, I think. And then we can have the Q&A later if you like. That would be perfect.
Well, yep. Okay, whatever. Yes, that suits you. I'll share then.
Yeah.
Okay. All right.
Thank you.
No worries. So Matt has given us a good introduction of where we were. I want to roll the clock back a little bit and talk about how we got there, part of our journey, and talk about our community participation. We're getting community to participate in stormwater management program. This talk will focus mostly on Little Stringybark Creek, because that's the project we led and the one I was more involved in. So the first question, of course, is why do you engage with the community? Well, that's because half of those impervious services are on private land. So if you want to do a total catchment disconnection, at some stage you are going to have to talk to those private landowners. Our private land community engagement program was a combination of education and incentives. So the education program was really important because in Little Stringybark Creek, there's only about 100 metres of the creek that is on public land, so most of it's sort of on private land. So we had to raise the profile of the creek. We also had to make people aware of the threats of stormwater, and also make them aware that they were part of the problem, but could also be part of the solution as well. And then we ran 3 rounds of incentive starting in 2008, and we had various lessons from those each incentive round, which is what I'll go through quickly now. So in round 1, we called Stormwater Tender, and it was a sealed bid uniform price auction, a little bit complicated sounding. In this program, residents developed independently their own bids after receiving a big information package from us. They identified what sort of stormwater control measure they wanted to put on their property. They engaged a plumber to quote, or multiple plumbers to quote on that, and they determined how much they wanted from us in order to build this stormwater control measure, typically a tank. Off the back of the millennial drought, we thought this would be quite easier, and indeed, of the 800 and so houses, we generated quite a lot of interest. Over a third registered their interest in participating in this program. But unfortunately, that didn't generate into a lot of bids. We only funded 54 houses in this first round. And that's because there was a lot of complexity in the application of this tendering process. So we had a bit of reflection as a team. We did some surveys, and we even had social scientists do some interviews of the participants and non-participants of the program. And what we found was the things that worked in our favour were obviously having financial incentives, the environmental elements of the project. People were interested in protecting their creek, and also the fact that it was a research project worked in our favour. What we needed to work on or do better was to create more trust in the community, both of the offer of a heavily subsidised tank and also the process that they had to participate through. We needed to reduce the financial outlay. So in the first round, people had to pay for the tank themselves and then claim a reimbursement from us. We had to minimise the risk associated with that, or the perceived risks associated with that. We needed to eliminate that big complexity, and also we needed to allow more time for people to participate. So this auction had an end date. Some people that just didn't suit. Life got in the way. So after that, we reworked the way we were going to incentivize people to participate. And in our second round from 2010 to 2011, we called Stormwater Fund. And this was a rising price auction. Effectively, we kept rising the price or the money that we would offer to residents, and they just simply opted in once the price was right for them. So this process was much more community orientated. The core of that was having a property appraisal with myself and a project plumber. So we engaged a plumber to work specifically with us on this project. And it was a simplified auction price format. Effectively, we filled out half of the forms for the applicants. At the end of the inspection, they would know what sort of tank they would have installed or what sort of system they would have installed, what the total cost was, and what we would contribute at that time. And then if that money wasn't enough for them, then they just sat on their bid and waited until the price went up, and we kept raising the price until we had spent all our money or had got enough bids in. Also important in this round was the money that we were paying to the Stormwater Control Measures were going directly to the plumber, so they didn't have to find that initial outlay as well. So although we had less interest in this round, we ended up actually with more installations. So we had 74 installations here. And these were arguably more cost efficient for us from a project teams because we were more involved in the design of the system. So in round one, we had some people installing, 50,000 litre tanks for 2 people just flushing a toilet. So they were oversized. But these ones were more efficient in terms of their sizing and cost. So again, we had a reflection. We did another survey of some of the participants or non-participants. The lessons here were the simple process was a positive. The community support, the extra involvement of the project team was well received. But again, we had issues of trust around the nature of these incentives, and obviously financial incentives was still a big barrier. So it was in the survey. The one thing that people said was the clearest reason for not participating was that the amount of money they had to contribute to install the tank. So in the third round, we were starting to get a little bit frustrated. Things were getting a little bit more critical in terms of the timing for the project. So we opted to offer free tanks to some of the properties. So those properties that were in what we deemed priority areas. So this was by far the simplest application process. 60-minute property appraisal. We discussed the options for installing a tank, agreed with the owner what a tank would be. Again, very cost efficient because the tanks were designed for the project, but with some benefits for the owner. And at the end of that 60 minutes, the owner just had to decide, or in weeks after that assessment, whether they were in or whether they were out. So as you can imagine, we had quite a lot of interest in this. By far, we were targeting less people, but we had a high interest rate, and we funded significantly more properties connecting them up to the system. So summary of results. So being adaptable in the process was really important. This was made possible for us because of the extended time frame of our project. It allowed us to target a diverse range of motivations, whether that be the community inclusiveness or the water savings or just the money incentives. We could overcome those barriers as they were identified. And most importantly, it gave us time to build trust with the community that the project was legitimate and that participation in the project was a low risk. Having a personable approach was really important as well. At first, in the first round, we were deliberately somewhat standoffish. We didn't want to be seen as imposing or pressuring people to participate. But clearly people appreciated having a face to talk to, someone that they could inquire with, and someone that they could connect with the project. And I can't say, what would have actually been good, I should say, meaningful financial incentives are absolutely critical. So not just a token amount of money. Installing a tank is expensive. You need to cover a significant chunk of that if you want a lot of people to adopt your tanks. Also, I would say that having some prior knowledge of the catchment would have been a bit more of an advantage. We did do a survey prior to starting any works. We asked in that survey how many people would like a tank. 86% said they would like a tank, but unfortunately we didn't ask them whether they would be willing to pay for that tank and how much would they be willing to pay. So that was a little bit of a missed opportunity. So Dobsons Creek learned from our failings there. They did actually develop a community profile and prepared targeted comms plans for that work, their work. All right, so that tells the story of getting the community involved initially, but how do you keep them engaged and participating for the length of the project? And that's really important because the systems do need maintenance and they will stop working if they're not maintained. So after several years of working in the catchment, we sort of started to ask ourselves, well, you know, we've got tanks in there now that are 5 years old. How many of those are actually still working? And then the more we sort of thought about it, then we started to ask ourselves these additional questions like, are the owners maintaining them? Do they know how to maintain them and when they need to maintain them? Are they even motivated to do it? Do they even care now that they've got their tank or they've got their money or so forth? So in 2017, we distributed or developed a self-reporting survey on the tank performance. We sent that out to all the participants of our program. It was an anonymous survey. People were given a small little token gift for completing it. It was 23 questions loosely around their house, the status of their system, and then sort of operation and maintenance. We had 156 responses, which is really good. So we feel like this is a good indication of what's actually happening in the catchment. In terms of motivation and satisfaction, 93% of respondents said that their tank is working. It's important that, 93% said that it was important to them that their tank was working. 78% were satisfied with their tank, and 70% said that they conducted regular inspections. So these are all very positive figures. The motivation for keeping their tank operational was that they were still keen to see the creek protected. They like saving water and they also like saving money. In terms of operation and maintenance, 79% said their tank was working, which is nice, a nice figure, high figure. And only 4% of those assumed that the tank was working. So we get the impression that people are aware or monitoring their tank. So they're confident that they know that it's working. Nearly 40 had said that it had stopped working at some stage or that they had made a repair. Okay, but what is a little concerning is the range at which it takes to implement those repairs, or for how long their tank is non-operational, between 1 to 1 year, 1 day to 1 year. So 28 days average. So a lot of variation there, a little bit concerning that there's tanks down for that long. What is positive, I suppose, is that only a small percentage were reported as non-operational. Still 15% is nothing to sneeze at. It is nice to think that nearly 70% were intending to repair those tanks in the future. A little concerning, though, that 30 perhaps weren't or were unsure if they were going to repair their tank. So there seems to be a little bit of a disconnect between the interest in their tanks. So people like their tanks, but it does seem to take time to actually effect a repair. And we wanted to explore this a little bit more. So what we did was ask them to rank a number of common household appliances and ask them to report how many days it would take them to seek a repair if it broke down. As you can imagine, the car, no surprise here, was the most quickest to be repaired, things like the washing machine. And unfortunately for us, our tank system was way down the bottom there. And that's not really surprising, of course. I mean, cars, washing machines, home heating on a day like today, highly essential items. If they break down, you address them quickly. Tank systems, not so much. Lawnmower, not so much. And what goes against the tank system is that they all have inbuilt redundancies. So if the pump stops, it switches back to mains water and your toilet's still flush. So it's something working against it, I suppose, have been repaired. So in summary, as I said, people like their tanks. They're very keen to keep it functional, but there are competing demands and it's time and money. And we label this the value action gap. Our recommendations is to recognise that at any one day, you're going to have a number of residential systems that are non-operational. Design the system. So you should design your whole catchment experiment with built-in redundancies if you can. But also we would encourage people, project leaders to have a program of ongoing engagement. So to make people aware that their tank, even after 5 years or 10 years, is still doing a good job towards helping the local creek, and also to engage with new owners, because there's a regular turnover, obviously, in home ownership in these catchments. And I think then that is my end of my slide.
Thank you, Darren. I just lost my, sorry. There it is. Well, that was great. And what a day to talk about stormwater. So we do have a lot of questions in the Q&A section. And though I think a couple of them have been already answered, I'll just put them here in case you want to elaborate on them. So this one is from Emma. She's asking if you have any comments on the number of properties or residents who participated. I guess Matt did mention from the project that was like around 200, 250 homes, but talking about both the catchments, what percentage was it? It was like 20%, 50% of the properties. And do you think it will be likely it will be similar in other areas, or was this influenced by any particular factors?
Yeah, so I think in Dobsons it's around 50% or just under 50% of participants, houses participated, and then in Little Stringybark Creek, so it's what, 230 of 800 or nearly 900. So, you know, between a third and a quarter. I can't do the maths in my head that quickly, sorry, but yeah, so reasonable amounts. I think would it be the same in other catchments? It's a really good question. I think from Little Stringybark Creek's perspective, lots of people, even though they weren't highly aware of the creek, they liked the idea of the creek being healthy. Some residents talked about, you know, in their youth, because they'd lived in the catchment for, you know, 30 years of spending time in the creek before the area was fully developed. So they had that connection to it. You might argue that it's as a fairly semi-natural catchment with lots of natural surrounding areas, that people who live there are more inclined towards these things. I don't really know. Yeah.
Thank you. And this one is from Eliza. She's asking if there's any potential of any of the stormwater control measures to have an adverse impact on base flow, where the focus is on harvesting, reuse, evaporation, etc.
That's one for you, Matt.
Yes, well, I mean, I guess you want to make sure that you're still keeping an eye on increasing base flows. And for example, those leaking tanks that Darren spoke about before, these tanks were designed to still have retention, so water that can be used in the home, still providing that benefit in terms of capturing water. But we also had this sort of water that was allowed to leak slowly into the rain, into the gardens and things like that, to still address those lost base flows. So of course, you definitely still want to make sure that you're not harvesting all the water and not forgetting about base flows. So, but I think from our experience, sort of not only here but also in other cases, it is pretty hard to sort of completely capture all the runoff. But I guess it's important, to be designing these measures to address all aspects of the flow regime. So.
Another one from Eliza. In terms of repair, what was the most common issue, like tank repair? Was it pump failure, or was it something else?
Yeah, pump was the biggest issue. I think like 90% of people reporting an issue was the pump, or included the pump. So yeah, that's the biggest failure. So again, that's a good advertisement for making sure that you're putting in quality products. Yeah.
Great. And Simon is asking if you can touch on the cost implications for new subdivisions and retrofitting to deliver the benefits achieved. Is it achievable without external funding partners?
Matt?
So I guess a case study to lean on is it's called the Aqua Revo development in Lyndhurst, Cranbourne. So that's a development that Southeast Water were the ones that did the development with Villawood property. And so it was required. So all new households in this particular development received a rainwater tank that was used for hot water. Hot water only. But Southeast Water paid for that system, and it was around the. I think Tim's here. He might be able to remember the price, but I think it was sort of in the order of $15,000 or $20,000 per household to have this stormwater treatment. Here it is there.
Yeah, I think you're right, but I think somewhere around 15 maybe. But yeah, worth noting, of course, that's like a highly conservative system in sense that there's multiple barriers in the treatment train and all that. They've gone really conservative because it's a pilot.
Yeah.
Great, thank you. And Emma is asking if any of the information from the smart tanks, any smart monitoring info was shared with the residents.
Well, we don't have any. There's no smart monitoring of the Little Stringybark Creek, or I think there was some in Dobsons, I think, but I wasn't involved in that. I don't know if anyone else in the panel knows the answer to that question. But for Monbulk Creek, in terms of the smart monitoring there's definitely individuals have a portal, a web-based portal that they can access to see what is happening on their tank and what releases are made from their tank and their contributions to the catchment. Yep.
Great. And I'm aware of the time. I think everyone will appreciate a short 5-minute break. So I'll just take one last question here, and then we'll try and address the rest of the question later, or maybe I can reach the participants through emails and, answer those questions. So this last one is from Adam, and this one's for you, Matt. He's asking if this research has been done in grassy ecosystems, something that they can learn. For, if I'm not wrong, Adam is based out of Bendigo, and a lot of systems that he deals with are grassy-based ecosystems with much lower rainfall.
Thanks for the question. There might be some. I'm not really sure of some examples. The other sort of examples of these catchment retrofit projects are mainly in North America. But yeah, maybe I can have a look to see if there are some examples. But sure, it in some ways areas of lower rainfall means there's less stormwater you have to deal with. So potentially could be easier. Yeah.
Okay. Well, thanks, Matt. Thanks, Darren. It's 11:26 now. Maybe we'll have a short 4-minute break and then come back at 11:30, and we'll start with the panel discussion then. Thanks, everyone.